morning, everybody, and I'm very sorry that for reasons that were quite unexpected, I had to cancel my trip, and I'm very sorry not to be there. I see very good friends in the audience, and I would like to have met, some of the students and hopefully newcomers to the field. And I also regret that there will not be an opportunity to see that beautiful part of the country that is so well known, so famous. So I have 3 lectures, and the first 2 lectures are on climate models. The last lecture is a very different one. Is on Lagrangian methods. Okay, so going to the first one. The first lecture is to review some of the real basic problems that I call challenges, maybe too big a word for this type of problems that confront the numerical analyst that wants to make a numerical model that is going to be used for climate studies. Okay, so far so good. Everybody can tell me if can you tell me if you see the PowerPoint well, and can you hear me well? Yes. All right. So then I continue on. Okay. So the two subjects would be we're talking about the advection equation and talking about the spurious mode in the advection equation that will motivate talking about computational dispersion. And these things will become clear as I go along. And the second one is talk about another concept that is very familiar to most of you, aliasing, but then the sequel that is nonlinear computational instability and how one of the ways to handle that problem. Okay, so we struggled quite a bit trying to put this presentation, communication together because when we started interacting, I could see you, the audience, but they couldn't see me, then they hear you and they hear me, and it was unclear until today, and thank you very much to everybody there in the IT department, that this can work that way. But as of yesterday, as of Friday, we didn't know, so it was unclear on whether you will be able to see me. So I had prepared a photograph of me in case you couldn't see me. So here it is, the photograph of me that I usually use in case when I have to give a talk and nobody can see me. Okay, okay. So the reference for my talk are in these 2 books. The first book is by Jacobson, and this book, material of this book came in large part from lectures that Jacobson attended when he was here as a student here at UCLA. The second book is by my former teacher and mentor, Eugenia Carney, sitting there in the audience. It has a very well read and known book. And the last one is an article that has appeared in the Encyclopedia of Atmospheric Sciences. I put here the first edition, and the second edition is on its way. Okay, so the climate models, but they should have been mentioned already, I imagine. But otherwise, what is the most popular application, if you wish, of these climate models? We mention usually the so-called IPCC. Okay, very well known to everybody. And what this project has done, this program. It has put together a group of modeling groups around the world. They have produced simulations of the climate that is with the computer, produced these representations of how the current climate is, and if the current climate from as obtained by the models is good, and one has confidence in the future projections. and one looks at future projections. So this map shows you, it's a global map, as you can see, and it shows a global projection of precipitation changes for the last part of the century in relation to the last part of the last century. So this is a prediction of how precipitation is going to change. But forgetting the details, these rectangles, these red squares of rectangles, mark regions in which only at least 1/3 of the models that are being run by different institutions do not agree on the projection. Okay, so there is a large uncertainty in the outcome of these models, and this is due to a number of reasons that perhaps we can touch a little bit. So what these models do is they try to reproduce the so-called general circulation of the atmosphere, and by general circulation is the time average planetary scale atmospheric motion that represents a long-term statistical behavior of the atmosphere. So we will use this acronym GCM, and in some cases we translate as general circulation model. That is the technical way. Sometimes we say global climate models. It is just about the same. Okay, and they can be used for climate or for numerical weather prediction. The numerical weather prediction that we have in the that is affecting all of our activities in the running the operational centers. Okay, now these models solve a bunch of equations, and these are the so-called primitive equations. And maybe in a few years from now, this is going to be changing, and this is going to be modified. But this is the way most of the models that are being running today, and they are written here not because I really going to discuss them, but show a couple of features. Okay, they have, of course, there is a term, as you can see on the left-hand side of the first and second equation, and some of the others, underneath. It's a time derivative with respect to time. It's a derivative with respect to time because obviously what we want is to predict. Okay, so we need an equation that gives us the change in time, and for example, in the first equation, the small u and the small u and the small v are the two velocity components in the horizontal direction. Okay, so looking at the second term in the equation 1, you will see inside the parentheses there is a u, and multiplying the parentheses there is a v. So that's the equation is nonlinear, or quasi-linear in this case. So we have here a system of equations that is nonlinear, and that is what adds to the originates many of the complications that we have in our field. Interestingly, as any physical system of equations, there are conservation properties. There are quantities that if the flow moves in a certain way, they are being conserved. So a fluid parcel will move around, and it will be conserved. And these are three of them. And in the particular case where the flow, let's say, very idealized, of course, flow, that there is no heating, there is no heat that goes to the air, there is no friction. Then there is a quantity that is called potential temperature that has something to do with the temperature that is conserved as the fluid parcel moves. This type of conservation properties of the flow are very key in what follows in the lecture. We are going to apply them, this concept, in what follows. There are, of course, integral conservation properties, but for that they will be more clear in the future during the talk. Okay, now there are a few ways to address the problem of solving these equations numerically. We are going to emphasize the solution via a grid. So we have a grid, and we have to discretize this equation by putting the unknowns or the variables in a grid, and here are some of the grids that are being used at this moment. Actually, the grid B, for example, is very much used in ocean models, whereas the grid C is used in many atmospheric models. And looking at grid B, you see that the two velocity components are defined in the center of the grid, and these grids are called staggered. And they are defined in the same point, which is great for those of you who have seen these equations to compute the Coriolis term. And and the H in the corner represents the so-called scalar variables, like pressure or temperature, or things of that, the specific humidity or things of that sort. Okay, so one distributes the grid, the variables in that grid, and this is in the horizontal. Of course, we don't have time to discuss the discretization problem in the vertical. Now, discretizing the equations replaces them by a finite number of algebraic equations, but it also distorts the solutions. This is a very simple, very simple example. Now, how do we approach the problem from a basic point of view? Is we linearize the equation. That is, we transform the nonlinear terms in linear terms. In this particular case, we are going to be very drastic and take just the equation 1 is the equation for Q, whatever the scalar quantity is, when is advected, so U, this capital U is a constant now. So it's a linearized equation, but the coefficients are constant. Okay, so the solution is trivial and is written in equation 2. And notice that these are Fourier components. You can see in the exponent kx minus ut, and all of these Fourier components move or translate with the speed bu. Okay, so the speed of all of the Fourier components that say represent the initial state of the flow of your field q is moving with the same speed. So that shape is not deformed as time goes on. However, look at what happens if you just simply take the derivative in space and transform it into finite differencing by taking the a center in scheme in equation 3. So you take q to the right minus q to the left and divide by twice the length of the interval. Now, in this case, the phase speed of each one of these waves now is given by equation 5. So we have u now, but it's multiplied not by 1, but by sine of the k delta x divided by k delta x. Now, obviously, if delta x goes to 0, the sine of k delta x over k delta x goes to 1. So that's okay. I mean, in the continuous case, we are getting back our original solution. But now each wave will move with a different phase speed. And it can be schematically put in this way. Okay, nu is in the vertical, and k should be delta x in the horizontal. And now for a given frequency, we do have two modes. Okay, one mode, that is the one in the left, is not indicated, is very close to the analytic solution, but the one in the right is spurious now, and is given to us by the grid. Okay, and even if you take a very a more accurate or let's say with higher truncation error representation of the derivative, you will still have this. And even in the limit, when you have a spectral model, so to speak, you still have that mode. Okay, so that mode has appeared. Now, when it can be a little bit more elaborate, I take exactly the same equation, but then go to equation 3 and put the time derivative also in finite differences. In this case, it takes a little bit more work to find the numerical solution. One can guess in equation 4 this expression with a lambda to the n, and you see this lambda to the n appears as an amplification factor. Okay, it's an amplification factor. And that can be solved, and in this case, I'm just jumping to the result. In this case, so what we are doing right now is we are taking both the derivative in time and the derivative in space. We have been written in finite differences, and now we have a C star. The C star that is in the numerator is the phase speed of one of the waves as given to us by the discretized equation, whereas C is the phase speed of the analytic phase speed, that is U. And you see that the curve, and of course when k delta x goes to 0, that is when we are in the continuous case, the two solutions are the numerical solution approaches the analytic solution. But as the k delta x becomes larger, now how can k delta x becomes larger? Delta x is fixed, say, so that k becomes larger. Now k is the wave number, and the wave number is inversely proportional to the wavelength. Okay, so the wavelength is becoming smaller, so k is becoming larger. So that means when we are moving to the right. Okay, so waves that when we are moving to the right in this plot are waves that are shorter. And finally, when we get to k delta x equal to pi, then the numerical solution doesn't move at all. Okay, doesn't move at all. Now, more interesting is to look at another feature that is called the group velocity. So if you have a group of waves now, they move with a group velocity. Okay. As we said before, in the analytic case, because all the waves move with the same speed, which is u, then the group velocity is going to be u or c, what we are saying now. And but when we discretize the equation, now we obtain a different value. We obtain a CG star. And the plot shows you the CG star divided by CG, again going to 1 when delta x goes to 0. Now, the interesting thing about this plot is that there are positive and negative values, as you can see. Now the range is not from 0 to 1, it's from 1 to -1. That means we have sometimes waves, group of waves that propagate with a velocity, okay, group velocity that is in the same direction as the analytic solution. But in some other cases, we will have waves that propagate energy in the opposite direction to the analytic solution. Okay, and that is these are the negative values. And even if we have an intermediate wave, that energy will not go away at all. Okay, will be there somewhere. So people have been struggling with these problems associated with these grids. Okay, let's look at this very well-known aliasing problem, and here I realize that I can also use my mouse to point. And here we can have a grid, and the grid here in X is the points that are either black or the circle. So these dots on the X-axis are the points in the grid. And let's say that we want to feed the system the wave that is represented by the thin line. Okay, but the grid is unable to see all of the details of this curve. We can see this point, obviously. We cannot see this point. Over here the grid sees a negative value. Okay, we cannot see this one. The grid sees a 0 here, and the grid now here sees a positive value. So for the grid, what we have done is we have given it the wave that is in black. The thick black line is the wave that is seen by the grid. Okay, and these expressions that are here on the slide, and that I imagine they're going to be available to you afterwards, these equations represent the way in which the grid misinterprets this wavelength. Okay, now. So let's go to with this introduction, let's go to the problem of nonlinear computational instability, and that has been a real problem in climate, because what we want to do is, as you saw in the very first slide, is we want to run this computer model for a long time. Okay, so it's not a matter of running for a few time a step and everything is fine, but we really need to produce long simulation, centuries, thousands of years of simulation, and we need to keep the situation under control. So to do this, to study this case, I have to introduce equation that now is two-dimensional. And this is equation that is equation 11. Equation 11 is in 2 dimensions now. So we again take a very simple approach to the flow. In the simplest possible case, there is only velocity, and there is no vertical dimension. So everything is a function of x, y, and t over here. But I have to introduce this quantity sigma or zeta, actually in equation 11, you can see the zeta. And this zeta is the so-called vorticity. And the vorticity is defined in this way. Is defined as this way this is the stream function. The vorticity here is defined as is a scalar quantity, is the curl of the velocity projected onto the vertical direction. Okay, so it's an indication of what the flow is doing in terms of rotation. And rotation in climate, in atmospheric sciences, in ocean sciences, being the flow on a rotating Earth, is our key quantity. It's one of our key quantities. So we work a lot with vorticity. Okay. Now the vorticity equation is relatively conceptually very simple. It says that the change in time of the vorticity in the left-hand side is given by the advection of vorticity. So the velocity dot the gradient of the vorticity. So what we basically are doing is we are moving vorticity around, with this equation. We are not creating vorticity to create vorticity or to dissipate vorticity. We have to add other terms to the equation that are dissipations or generations or things like that. So now we are dealing with a system that cannot create vorticity. Okay, just can only move it around. Okay. Now, one way that the numerical analyst has used to formally write this equation is equation 12. Okay, equation 12, meaning the right-hand side of this equation is written as with this expression J, which is a Jacobian, and the Jacobian quantity is defined here in the bottom. Is defined as the derivatives, as a product of derivatives of the functions that are inside of the Jacobian. So this really is an equation on the stream function psi, if you want. Physically, the stream function is a field that if you take constant lines of the stream function, the velocity is tangent to these lines. Okay? Now, the vorticity, zeta, is the Laplacian of the stream function. So this equation 12 is really an equation of third order with a time derivative of a Laplacian equal to the Jacobian time. Okay, now this Jacobian satisfies a certain number of analytic properties that are very simple to demonstrate. And they are, for example, the mean on a domain of this. I'm talking about the equation 14. The mean of a domain of the Jacobian of two variables is 0. And from now on, and you will allow me to do this. It's a simplification in the boundary conditions. We will assume that the domain is periodic both in the x and y directions. We many times use that because, after all, we are working on Earth, and that's a bit periodic in the two directions. Also, equation 15 is that if we take the Jacobian expression and we multiply by either of the functions, and then we take the mean in the entire domain, this gives the same value. So based on these properties, and you will see along the notes that I have indicated in some cases exercises to prove, because they are analytic expressions that are simple to prove, then one can show the last three important relationships in that page. And they are really physically very simple. The first one says that the time derivative of the mean vorticity is 0, right? That is, if you take the mean vorticity and the entire vorticity, in the entire domain, you compute the mean, that quantity doesn't change as a function of time. The second one is that the time change of the mean vorticity square is also 0. So again, computing the vorticity square, okay, which is positive, is a positive definite quantity, but nevertheless, I mean, it doesn't change in time. And you can expand that, you can say that to the n if you want, to the n, but then it's an integer. And the last equation, it says that the time derivative of v squared, the gradient of psi, the string function, which is the velocity, so the velocity square mean is 0. So the second quantity, in the second equation, in the equation 17, this quantity, in the equation 17, this value, this expression, say the square, is called entropy. Okay, so in words, we will say the entropy of the system is conserved, or it doesn't vary as a function of time. And in the last equation, it is the velocity square. So this is a simple statement that the kinetic energy of the system is conserved. And obviously, I mean, there is no dissipation, and there is no generation of kinetic energy. So these are expected, quantities. But of course, these are functions, these are constraints that are satisfied by the analytic system. Okay, now let's see what happens if we start discretizing. And here we have ways, there are many ways of discretizing these derivatives. For example, look at the grid on the left. In the grid on the left means we have to compute derivatives of the function psi in x and in y, and derivatives of function psi in x and in y. Okay, so if we fix in the point in the center here, we can use these points to the right and to the left to do the derivative with respect to x, and above and beyond to compute the derivatives with respect to y. Okay, that's very simple. In this one, in the second one, we will use the points to the right and the left to compute the derivative with respect of psi with respect to x. But if we want to compute the derivative of theta with respect to x, we will take this point, and then we take the average, and we will represent the vorticity in this point of the average between the two. So we use the vorticity and we distribute the vorticity and the string function in different ways. Okay, and then we get different expressions. And one example is written down there as J1. Okay, now let's see. Let's see what happens in this case. Okay, so that we have this expression for the vorticity equation, and in the bottom we have the expression that gives the vorticity as the Laplacian of the string function. Okay, the very simple expression for the Laplacian, infinite differences, and this is the problem we want to solve. Okay, so years ago, of course, but it's such an elegant solution that I really would like to show it. I mean, Phillips in 1959 gave a very, very elegant example of how aliasing error can cause computational instability in this problem. And for that, he says, okay, let's look for a solution of this system of equations now, that is a discrete system of equations of this form. Okay, psi of ij. Notice the ij now as a subscript, so in the point I and j of the grid. And that's what we are trying to find, assuming that these solutions satisfy the initial conditions, of course. So we want to find this C, S, and U as a function of T. We want to find these expressions. And then we say, are there expressions like this that satisfy, that can be chosen so that this particular function really satisfies our equation? Okay, then just start manipulating, just replace, and you get equation 22. But it turns out that in equation 22, there are waves that are too short for the grid to obtain. And in that way, the grid misrepresents some of the terms in the right-hand side of equation 22. So for the grid, the equation 22 is really equation 23. Okay, equation 23. And because of that, when one tries to find C and S and U, the solutions are big U, that was a function of T at the beginning, you say, is a constant. It didn't appear actually in equation 23. It's a constant. It's a constant in time. It's a constant that we have in the initial conditions. But C and S, and in particular C, has in the left-hand side, I don't know if you can see, I mean, it has an exponential in time with a positive value. That means this solution is going to blow up, okay, in time. So the grid solution, despite the fact that the vorticity square in the continuous system is conserved, then the vorticity square in the numerical system is going to blow up. And it doesn't really matter whether we decrease the interval delta x or the, in this case. Okay, we haven't even discretized in time either. Okay, so this is a problem that the grid that we will have in whatever we do with the so-called precision or resolution of the grid. Okay? Well, there is a way to work out, and here again is for your information. There is a way to work this out and come up with some analytic conditions for this so-called Jacobian to be such that these instabilities do not occur. And in particular, if you use expression 30, which is a kind of interesting because you define a Jacobian, which is the 1/3 is the average of the Jacobian J1, J2, and J3. All of these Jacobians, so you can imagine it's a very long expression. Okay, if you define that one, then the entropy and the energy of the system are conserved. So that was a way to get around the problem of linear computational instability. That's a result from a real integration of the entire equation, and that's, for example, an entropy average in the entire domain, and you have the Jacobian J1, that is the one that we saw at the beginning, is the black line. If you integrate in time, that is this line. So in time, immediately the entropy starts growing, and it becomes unstable. Okay, and this Jacobian JA is the unfortunate choice that we made in this slide was to make it yellow, so we don't see it very well. But it's hidden, somewhere over here, the yellow. So it's a constant, as a function of time. Okay, so that's one way of writing define different equations in such a way that the analytic constraint is satisfied. So you can imagine what we have been doing is basically saying, okay, we take the vorticity at each point in the grid, okay, that we calculate with the numerical method. We take it square, we add it up, okay, and there are cancellations between different terms in the equations so that the summation becomes constant in time. Okay? So this delicate cancellation that can all be expressed in analytic terms, as we said before. And this is the energy. The energy is more interesting because it's easier to conserve energy than to conserve energy, entropy. So again, the Jacobian J1, for example, will be a recipe for disaster. Okay, so we are becoming to the last part of the talk. And so it's talking about a few things that are happening right now. So one of them is that it is represented by the figure on the left. You see, whenever I wrote the primitive equations at the beginning, they were written in so-called spherical coordinates. Okay, the spherical coordinates, and the variables were latitude and longitude and height. Okay, but defining a grid on the sphere brings up the so-called pole problem as the meridians converge as one goes towards the pole. Okay? And that requires usually combination of approaches when we deal with these models, with these grids. One example is to get from the very early times in the general circulation modeling of the atmosphere, was to define grids that become less and less dense as one moves towards the pole. And there are others that have been used more recently. Okay, the one on the right-hand side is another grid that tries to avoid that problem by not having it. And this is coming from an isocahedron grid, I think. I know that Michael is in the audience and he will correct my pronunciation properly. And you see, this is the Earth is divided in hexagons, basically. So there is no location for the pole problem. Now, when one deals with this type of grid, then you get the same problems that we had before. So these Jacobians have to be written now and with the same philosophy, okay, in such a way that the quantities are conserved and so on and so forth. There is another approach that is very popular and is referred as the spectral model. So going back to our equation, we had the vorticity equation. And the vorticity equation, you might remember, the vorticity was the Laplacian of the stream function, okay? So that would be so nice to have the function, let's say, the stream function expanded as the eigenfunctions of the Laplace operator. Because when we do that, the vorticity becomes just simply the stream function times constant. Okay, so that's one approach. And over there you have this very long Fourier series. Well, it's an infinite Fourier series, of course, when one is expanded. Mind you, here this expression in the bottom. Okay. This is psi of x, y, and t expanded in sines and cosines. Okay, and this is a double Fourier expansion. But this is not very general. I had to warn you, this is not very general. This is for the flow in a channel. Okay, the flow in a channel, then this expression will satisfy the boundary condition for the flow in a channel. But that's enough to satisfy, the point that I want to make. Okay, now when you do that, then you can compute the Jacobian again, and the Jacobian appears as this double sum of the terms that these small a's squares that are over there are these eigenfunctions of the Laplace operator. The point is that there is a C. You can see the big C over there. C it has three subscripts. So C is really a three-dimensional array. Okay. So by doing this expansion, one can start increasing the number of waves that you include in the truncation. The matrix C becomes larger and larger. So it becomes enormous. At the end And that makes the problem very cumbersome or impossible to deal with. So one way to go around this problem has been to actually compute the nonlinear terms in the equation on a grid, and compute the linear terms in the spectral domain. Okay, and these are semi-spectral models. And these are very much in use. Many of the big centers around the world are using this for not only for this reason, but there are other reasons. Like, for example, one can take the say the time derivative and use longer time intervals. It's a matter that we cannot really discuss today, but I'll be happy to to answer by email some questions on this. Okay, so to finalize, there's another group that has become popular, a group of methods that have become popular, and these methods are called semi-Lagrangian integration schemes. And what it basically we do is the following: you have this function of t plus delta t. So we have to find the value of the function f at t plus delta t, knowing the function f at t, okay, or at t minus delta t, if you want. Okay, so what you do is you take the points on the grid, which are these points, we call the arrival points, and then you project them back in time, and then you go back in time to where they were at time t. And at time t, you know the values of the function f in the grid, okay, at time t. So you know values here and here, so you do some interpolation and you know this value, and if there is no the value here in the point that I'm indicating right now, and if there is no friction or dissipation, this value will be conserved, so this is going to be kept constant as you proceed to the time t plus delta t, okay? So that's the principle, and of course the devil is the details. Now the application is difficult. There's a lot to discuss about this, but I just simply want to show some of the solutions of this obtained with this method in comparison with another method like the one that we did at the very beginning, just to find the differences. And that is for an initial value problem, and just to take this one on the left, is the initial value is this triangle. The initial condition is in this triangle, and in the analytic equation in the analytic advection equation with constant coefficient, then everything goes the same. More just translates. But in a numerical solution, then this is the numerical solution after so many time steps. The numerical solution is totally distorted. And it gets totally distorted the same way if we use a numerical scheme based on the grid points or the semi-Lagrangian numerical scheme. So the real advantage of the semi-Lagrangian schemes is that you can use an interval of delta t, which is much longer, and that is the really use of these methods. Okay, so let me summarize, and we have a few minutes for questions, and I'm pretty sure that with the delay and the 15 minutes, I think that we were running late, I was told earlier, and it's time for lunch. So you might be looking forward to the restaurant. So let's say that you will appreciate finishing early. So the summary is as follows. You have reviewed selected challenges in the numerical methods used in general circulation models. Okay, in a very highly idealized context, but that's the way it's done in general. That's the first step. When you choose something that you can actually do by linearizing the equation, by taking constant coefficients, in the assumption that when the problem becomes complicated and nonlinear, then you will have, at least in some limit, in the limit of the small perturbations, your equations are going to be representative of the problem that you are dealing with. Okay? And so what we have done is we have shown that there can be frequencies, spurious frequencies that appear. Okay? Spurious frequencies just because of we have discretized. We have waves that, or solutions that because of the grid, they are distorted, and either sometimes they don't move, sometimes more, they propagate energy in the opposite direction that the analytic solution should do. We look at the so-called nonlinear computational instability, and this is a real problem. Usually when one runs a model and the model becomes unstable, the first thing that one does is to decrease the delta t, or to decrease the delta x, or to increase the delta x, or whatever. And now that doesn't help when there is a nonlinear computational instability, because the flow becomes unstable anyway. So what is the approach? Well, there are several approaches. Some of them, in case of the spectral method, for example, is much easier. I discussed the specific case of the grid point methods, in which you design your equations in a particular way, so the equations try to satisfy as much as possible the numerical equations, as much as possible the constraints, the integral constraints of the analytic equations. Okay? There are several approaches. Then there is computational dispersion. There are, again, several approaches in the literature. This is very interesting field of research. I mean, how you can minimize the computational dispersion, meaning the waves behaving in a different way of what they should. Okay, now now here comes something more specific to our field. When one designs a numerical method for GCMs, one has to take into account that we are also working with just a little bit of the problem. I mean, there is a huge part of the model that has to deal with the physics, okay, with the physics. And in particular, we have been cursed with dealing with the moisture. And moisture, sometimes small differences in the temperature, say, determine whether moisture will convect, will produce convection, will precipitate, by changing phase, then it gives heat to the atmosphere, and the motion can be amplified, and so on and so forth. Okay? So the errors, the smaller errors in the physics, can become much more important in this context than in the simple context that was showing in a curve that one grid produces less errors, or the magnitude of the errors are smaller than another grid, that another methodology for numerical implementation. For example, if we use a spectral decomposition of the topography, say, okay, and of course we will get the oceans very flat, as they should, and the mountains very steep. But if we truncate that, then we start getting deep holes and valleys in the ocean too. And these things usually, if the resolution is low enough, may be of concern. So my conclusion here is, I'm pretty sure that you are going to understand all of these methods. Just taking these slides and looking at the equations, it will be very simple. However, the communication between you and the mathematicians and us is necessary, because designing method to be used in numerical models require both mathematical insight and physical insight. Okay, mathematical insight for what is done in terms of the frame of mind of integral constraints, of the Hamiltonians, if you may want, but also you need to have the physical insight. What is really needed in our field? And so the collaboration has been required, and frankly speaking, the collaboration between mathematicians and mosaic scientists or ocean scientists, when it has occurred in the proper way, has given us very beautiful results. So thank you very much.